we'll talk about diffusive burning, first of all, of liquids and solids, and then we'll talk about, that'll be a nice transition to start talking about flame lengths and plume heights, where we can then talk about the impact of the burning process on the overall compartment. To get us started, I'd like to take a look at a video that shows, again, this evolution of a small fire where we get an initial ignition process on a solid to the point where this becomes what's called a room and contents fire, where the room is completely engulfed in this burning process. So let's switch over to the desktop, and we'll take a look at, again, one of these videos that's been provided by the National Institute of Standards and Technology, where we'll see that there's a small ignition source on a sofa. So it's this living room fire. So this mock room, so it's a mock-up of a room. It's been designed where there's a small ignition source on a sofa. And what you see is that you get this very small flame that is going to spread. So we talked about flame spread. So the things that we've talked about so far, we've looked at what the ignition process is for a solid. We understand that the ignition process is a heat transfer process where at the simplest level, what we need to do is to identify time required to heat the solid to some ignition temperature. Again, this is an empirical value. We understand that in reality, there are detailed mass transfer, heat transfer, and chemical processes that actually allow the development of that initial flame. Now, we see that there's a spreading process, and again, we've talked about flame spread from the perspective that this is now a continuous ignition process where the flame is searching for additional sources of fuel, and this pyrolysis front is moving on the condensed phase. So at this point, so 11 seconds after ignition, this combustion process, this fire, this small flame really, is unaware of the extent of the domain. So there's no awareness of the fact that it's constrained within this room. It's burning openly, burning freely on this sofa. So let's continue. As we expect, the flame spread process is much faster vertically. We talked about that in one of the last lectures because, again, the buoyant transport heats up the sofa preferentially in the vertical direction. You see that the lateral spread is much slower. Now, at this point, about 30 seconds, the radiative heat flux from this flame is significant enough that it's really starting to impact and preheat other portions of the flame, of the sofa, even where there's no direct flame contact. Now, one of the things that we oftentimes say in terms of fire, so you're starting to see this wispy smoke coming off of here, is that for a typical room like this, a garbage can fire or something slightly smaller, which this is about that size, perhaps even larger than that really, should be able to set off a smoke detector located even far away from this fire. So at about 50 to 100 kilowatts in terms of the heat release rate, which is really not that much in terms of a heat release rate, we should be able to have set off by the smoke and these soot particles that are generated a smoke detector that's at some distance away from this initial ignition process. Again, the acceleration and growth of this fire is related to the heat transfer processes that it's impacting this sofa with. So the flame is, and the fire now is beginning to significantly affect the heat transfer processes further and further away from where it is directly located. There's a growth in the heat release rate. We're seeing now a real development of perhaps an upper layer. Now, at this point, I think this is sort of an important issue to think about. We can still see the ceiling. We can still see the details of the wall-ceiling interface. And radiatively, the fact that we can see it means that it can see us. So although the smoke is starting to obstruct this view somewhat, for the most part, even in the visible, we're able to see through this smoke and see the ceiling. And this is still a cold ceiling because this is a relatively thick material. It's this gypsum board, most likely. And so this thing is still relatively cool. And so radiatively, it's cool. You know, the radiation heat transfer from any location in this living room to the upper layer is still probably dominated. It is, in fact, dominated by the cool ceiling temperatures. Again, we allow this fire to continue to grow, and there's further obscuration of the upper layer. We see this ceiling starting to fill with this smoke. At about 1 minute and 33 seconds or so, we can no longer see the ceiling. And so, not saying again that this is now becoming optically thick in the radiative sense, but it's certainly in the visible, it's thick enough that we can no longer perceive details of the ceiling assembly. And of course, there's rapid growth in the fire. Now, you're going to see that you see the layering here. So by 2 minutes or so, you see a distinctive layer between the relatively cool lower layer and the hot upper layer. This is, again, from a modeling perspective in fire, we oftentimes use a two-zone model where we model the cool lower layer as one zone and the smoke-filled upper layer as a different zone. Now, as this filling in process takes place, we've talked about this before, but this hot upper layer now is radiating significantly to all portions of this room. And again, it's becoming optically thick so that at some point it would be a reasonable approximation to think about this as a black body at some average temperature. There are several implications to that, one of which is that the pyrolysis process is going to be non-local, so it's no longer anywhere related to what's occurring with this primary fire. The other issue is that as we're releasing volatiles from even this direct burning area and adjacent areas, the flame length that would be supported if we had a burner that is producing the amount of volatile mass fraction of mass flux, the overall mass transfer rate or mass burning rate associated with what this scenario is occurring, the flame would likely be much higher if it were in the open. But the issue is that because we're trying to burn in this low oxygen environment, so because we have this smoke filling from the top, we actually get more incomplete combustion and a lot more products of incomplete combustion transported into the upper layer. Those products of incomplete combustion include carbon monoxide, which itself is a fuel and which can burn in other regions. And so once we start banking down this upper layer in such a way that it inhibits the overall sort of proper burning of the fuel and to get a complete combustion products evolving from it, we're actually creating a more hazardous upper layer concentration of gases which can burn somewhere else. Now, as this thing continues to grow and heats up this upper layer, and this upper layer again banks down, and we'll see that there's significant heating that's going on of this adjacent, we see melting and warping of this lampshade. We're going to see volatilization and delamination on this sofa that's next to it. So you're starting to see vapors that are rising from this sofa, again, that have nothing to do with this fire, but have everything to do with the heat transfer from the upper layer. So we see that process occurring. So all these volatiles and fumes that are evolving from here are associated with it. So in all of these processes, the thing that we have to remember is that the burning process, so you see that delamination there, vapors are evolving, etc. So what we want to do in this lecture is we want to describe the actual burning process of a solid, understanding, you see this ignition process that occurred here, you see this delamination. So we're getting really flashover conditions here. You see all the volatiles that are evolving from there. And at this point, the ventilation is occurring such that where cold air or cooler air is feeding in there, the hot products are coming out, and this is a flashover scenario. Okay, so we need to develop an understanding of what controls this diffusive burning process. And to start, really, we understand that we're focusing on non-premixed flames. We said a non-premixed flame is an interface between fuel and some oxidant. And the reality is that even in industrial flame applications, it's preferable to use non-premixed flames because whether you're looking at a coal power plant or a natural gas burner system, you have high radiant output, so the soot particles allow you to get a lot of radiation out of this system. Have really good turn down ratios, and so what does that mean? Well, one of the things that occurs in terms of the stability of premixed flames is that if you want to get more heating in a premixed system, you have to turn the velocity of the fuel and air mixture. You have to increase the overall flow rate. But what happens is that if the flow rate is mismatched to the flame speed or your ability to stabilize the flame, then you have all sorts of stability problems with premixed flames. On the other hand, with non-premixed flames, I can always increase the amount of fuel that I'm going to burn, and it's simply going to increase the flame length. So the turn down aspect of it is the control aspect in terms of stability. So this is really a stability control issue. It's inherently safe relative to a premixed flame. One of the things we talked about in premixed flames is the need for a flame arrestor. Remember that discussion? We talked about the fact that if you, and this is somewhat related to the turn down issue, if I have a premixed flame burning, so I have a fuel air mixture that's burning, so fuel and air burning in a premixed fashion, if I reduce the flow rate, what's going to happen is this flame is going to propagate back into the tube. And if I have a plenum where, for example, I was doing my mixing somewhere upstream, if I get this flame to propagate in here, I'm going to get the potential for a catastrophic failure of this plenum, of this pressure vessel. And of course, that's not desired and is a big problem. When you have so what typically will happen in a premixed flame system is the need for these flame arrestors to inhibit the flame propagation into the plenum. Remember, the flame arrestor is just a quenching process where we want the flame to extinguish, the premixed flame to extinguish before it travels into somewhere we don't want it to go. With a non-premixed flame, there is no flame speed, so there is no we're not expecting, unless, again, some misuse of the system, the fuel and air to be pre-mixed prior to reacting. Now, having said that, there are problems with non-premixed flames, and it's the fact that there are incomplete combustion products that are produced in these systems because of the poor mixing. And so we produce lots of carbon monoxide, lots of soot, which can be good in certain scenarios, for example, when we want to get heat transfer. But obviously, from a fire perspective, these things are negatives and pose hazards. So this is just, again, a non-premixed flame where there's some fuel that is being consumed, and really what we're seeing is really the outline of the reactions, and we're seeing strong radiation from the soot particles inside. There's so many particles, so many soot particles, and so much soot that they punch holes into in the flame and escape. So under certain conditions, you can oxidize the soot particles, and then you don't get smoke afterwards. But in cases where you do not oxidize it, you produce this smoke. So if you oxidize soot, I'm going to do it differently. If you do not oxidize soot, you get smoke. And that's what we're seeing here. And if you do, you just get just carbon dioxide and carbon monoxide out of the system. Okay, so one of the sort of theoretical constructs and underpinnings for understanding diffusive burning is the laminar diffusion flame. And the laminar diffusion flame is the simplest, or one of the simplest types of flame systems. And we'll see, I'll have lots of pictures of this system, but really what we have is a molten system, and it's molten because of heat transfer from the flame. So we have a flame supported above a fuel source, heat transfer from the flame, melts, causes the phase change in this fuel, in this condensed phase fuel, capillary action wicks it into to higher elevations in this wick, and again heat transfer from the flame vaporizes the fuel and allows that fuel to burn with oxygen that is available externally. So that's one scenario. Another type of diffusion flame is a droplet flame. So whether, for example, if you were examining in detail a compression ignition engine, a diesel engine, there's a fuel spray. So there's an atomizer that sprays out fuel spray into this hot environment, and you get ignition of these. And one model, one concept of what this looks like, it's complicated, but is that you have these droplets evaporating within some flame envelope. So the droplets themselves are evaporating, they're creating gaseous fuel. That gaseous fuel is again reacting with oxygen that's external to this flame sheet. Another sort of simple way of looking at diffusion flames is something called a counterflow flame, and this is a research configuration where we have an oxidizer flow that stagnates with a fuel flow that creates this stagnation plane, and also allows a nominally one-dimensional flame to exist between the two flows. And what that's useful for is for probing the temperatures and species in these flame systems. So people will use all sorts of different diagnostic systems to understand the details of flames in such a configuration. Everything, again, from sort of laser induced fluorescence, different types of laser-induced sort of population changes, so they can see photons coming off of the different activated species. Okay, so the thing that I want to convey and make sure that it becomes clear is that for all these problems that we're talking about in terms of diffusive burning of solids, and this is the key in solids, the heat transfer controls the mass burning rate. And so here's, again, a simple rendition of that. If I have some solid object, some condensed phase material, and there is a continuous burning process where there's a flame, so this is supposed to represent a flame here, above it, it is in fact the heat transfer from the flame, both radiative and convective, that initiates and allows for mass flux away from this solid. That mass flux that we've talked about this before is of what might be called a pyrolysis gas, might call it a pyrolysate. So it's the gases that are evolving from this decomposing solid that are the fuel that burns at the interface with the oxygen. So the fuel that's liberated by the thermal decomposition of the solid burns at an interface with the oxygen that is external to it. The feedback from this burning process, because this creates high temperatures, the feedback from that to this relatively cooler solid is what causes the decomposition, and obviously that's the cycle that we're interested in. And we already pointed out that the candle flame is one example of this, and that a droplet that's burning, a fuel droplet that's burning, is another example of this system. Okay, so more details on sort of the structural issues of these burning problems. And again, this is either a liquid or solid. So this is just, again, generally condensed phase materials. So we have some liquid fuel droplet, and we imagine that there's a flame that's been supported around it. Imagine this is in a microgravity environment so that you get a spherical flame around this droplet, so there's no buoyant distortion of it. So whether it's in microgravity or zero gravity. So as an idealization, so no buoyant. Okay, so in whether you might think about it as non-dimensional temperature and non-dimensional, well, these are non-dimensional, but mass fractions also. If we're to take a look, if we say that we center the this axis on the fuel droplet, and we look outside and we make measurements of temperature and measurements of different mass fractions of the components. So yi is the mass fraction of species I. What we would see is that we've already talked about the fact that it's the interplay of the heat flux that generates the mass flux that controls the burning. So we've already said that. But what we would see is that there is a mass fraction of fuel at the interface, at the droplet interface. I should really have done this. So this is one inside. So it's a single component droplet, and then there's some mass fraction beyond that. So if I really centered this on that, there's obviously some droplet RD, some droplet radius here. Okay, So there's some mass fraction of fuel at the interface, and diffusional processes will allow that fuel to be transported to the flame sheet. So let me just write that. Diffusion or diffusional transport takes the fuel molecule to the flame sheet. And so you might question, well, why would it take it to the flame sheet? Why is there a gradient where the diffusion can act? Well, earlier on we said that I think we said this. I hope I said this. Well, maybe I'll say it now. That the reaction rate in these systems looks like YF, YO. This is sort of a simple description. Exponential of minus E over RT. So this is that Arrhenius law. Now, in a scenario in which reactions are much faster than the transport timescales, so when reaction time, characteristic time, is smaller than transport time, the flame is infinitesimally thin, and YF and YO cannot exist together, and it's an idealization. It's a mathematical construct, but it is very important and useful in sort of the basic issues in detailing combustion and diffusion flame analysis. And this is sometimes called the fast chemistry limit. And so in this fast chemistry limit, what happens is that once we go to the flame, YF goes to 0, and YO2 goes to 0 on the other side. So at the flame, YF and YO are completely consumed, and on both sides of the flame, neither of them exist sort of where they didn't natively exist previously. Now, that's certainly not the case for N2. N2 is conserved in all this. So N2 doesn't react in the simple problem that we're talking about here. And so from that perspective, N2 can live all the way to the droplet interface. So the N2 diffuses to the droplet interface. It's impermeable in the liquid, in this droplet, but again migrates through the system. The products are created exactly at this interface. So what we really are saying is that the reaction rate, one model perhaps for this, is that the reaction rate looks like a reaction rate perhaps per unit area that's specified as Dirac delta at RF. So there's this infinitesimally small reaction zone located at RF that consumes the fuel, consumes the oxidant, and produces the products. So this is again sort of like an idealization of what this might look like. Okay, so products are produced, they diffuse to places where they did natively exist, so far away from the droplet and towards the droplet. And the temperature, because the energy release rate in the energy equation basically looks like W triple prime times the heat of combustion. This also, that source term occurs at the flame sheet, and you get this diffusion process down, and it's that diffusional heating of the droplet that causes a temperature increase, which of course is what is responsible for the high mass fraction of fuel at the interface. So we've spoken and discussed in the qualitative sense what some of the issues are here, and so we might have some practical questions as to how do we actually calculate things. So given some material, whether it's a polyurethane foam or some other material, how fast does it burn? What's the heat release rate while it's burning? If we were to cool the surface, would we suppress the flame? This picture is of a combustion testing device called a cone calorimeter. And it's called a cone calorimeter because there's a radiant cone-shaped heater system so it's a cone heater under which, so there's a well-specified heat flux on some sample that's located under the heater. The sample is typically on a load cell. There is an igniter located above the sample, and the types of things that are measured from this are an ignition time for some heat flux, a surface temperature at ignition, the mass loss rate of the sample from the load cell, and the heat release rate. The way the heat release rate is measured is once this sample starts to burn, the products of combustion are collected and a gas analyzer system analyzes these products. Now, I think we've mentioned this, but I'm just going to go through a couple of issues about this. You would think that this heat release rate, that the easy way to get the heat release rate is to figure out this dmdt, so the m dot of fuel that's produced, and multiplying by the heat of combustion for the material. The problem is that oftentimes we don't know what the heat of combustion is for any particular material. In fact, the way we find the heat of combustion is by doing the measurement that we're talking about right now. So this would be great, but we don't know what this is in general. Another possibility would be to measure the amount of heating that's done here. So you'd say, well, if I put maybe a thermocouple up here in this gas system, maybe I can just do an energy balance and figure out how much heating was done so that I can back out what the heat release rate is. So basically, sort of conceptually and from a flow perspective, the idea would be that I have a flow of cold air. I can think about the fact that I'm injecting some fuel into the system. I get burning. I measure the temperature somewhere over here. I draw some control volume here, and I say that the enthalpy in is equal to the enthalpy out and plus whatever energy addition that I put in, and I can figure out what the energy release rate is. So simple energy balance on the system. The problem with this is that there are all sorts of parasitic losses. I mean, It's very hard to insulate this thing well enough. There's radiative losses. So this is a very challenging system to do this. And one of the early calorimeters was called the Ohio State calorimeter, which is the OSU calorimeter, and it was based on this energy balance idea. What the cone calorimeter, what the innovation that came about in the development of this at NIST is the idea that the heat of combustion on an oxygen basis, I think we talked about this, is always about 13 megawatts per kilogram O2. So if you know what the heat of combustion is on an O2 basis, which is relatively fixed, as compared to the heat of combustion on a fuel basis, which is variable, which is, has a wide range of values, then really what we want to do is we want to measure what the mass flow difference in the oxygen is between the inlet and the outlet. So let's see, diagrammatically, we have to measure the overall mass flow rate. We know what the mass flow rate of oxygen is, say going into this system, because we know what the fuel flow rate is. So here's our burning process. And somewhere down here, we know what the overall we know what m dot total is, because we measure the volumetric flow rate and we know the temperature, so we can figure out the density. We measure the oxygen concentration, so we have m dot ox in and we have m dot ox out. And so we relate Q dot to the change in the mass flow rate of oxygen times the heat of combustion on an oxygen basis. So that's the underlying model for that cone calorimeter system. All right, so let's go back to the diffusion flame and understand what some of the driving issues are, again, in this diffusion flame analysis. So this is species conservation, and so let me walk you through what this means. So this equation, it's a one-dimensional formulation, steady, and it tells us in this 1D Cartesian geometry that there's a bulk flow process for the mass fraction of the fuel, there's a fixed law diffusion process, and there's a consumption process that occurs somewhere in space. And the somewhere is dictated by where the temperature is sufficiently hot and where I have some fuel and some oxygen. Now, what I was alluding to earlier in terms of the discussion about timescales is this. You can think about this bulk flow as a density times, so this is a scaling analysis. So algebraically, we're looking at this problem. So when you think about a length scale, dx, divided by the velocity, that is a flow time. So this bulk flow term can be interpreted as the mass, the density of the fuel divided by a characteristic flow time. Similarly, the diffusion term can be interpreted in the same way. It's a mass of the fuel mass concentration, the fuel mass density divided by diffusion time. And the reaction's obviously similar as divided by reaction time. Now, if we assume that the reaction time, and this is the case if you put characteristic values in there for combustion, we find out that the reaction time is much smaller than these other times. And so when we multiply by the reaction time, in sort of a weak asymptotic analysis, I mean, we're not doing a full asymptotic analysis, what you see is that these are, say, order epsilon. They're much smaller than this term. So the dominant term, the dominant balance, is the reaction term. Well, it says that the reaction term is identically 0, and that's a little bit disconcerting, but there's a non-trivial interpretation for that, and the non-trivial interpretation is that the fuel and the oxygen don't coexist, and this is what we said earlier, that there's a thin region where, very thin region, where they do interact and where they balance diffusion, but from sort of like the outer scales, from an outer model, these things are not important except for, this reaction term is not important except for in this thin region. And so maybe the other way is what we said before, is that you can think about this as delta x minus xf. So reactions only occur in a thin region, and in that thin region, YF and YO are so much smaller than their values anywhere away from there that we can essentially disregard that region compared to everything else. Okay, so we want to build. Oh, I know we want it. This is where this analysis, this class is getting more and more complicated because we're looking at more and more complex issues, and you'd have to see this many times to obviously to become truly comfortable with it, but hopefully we're able to give you enough insight into some of the overall issues. So what we want to do is we want to draw an analogy between the evaporation problem and this combustion problem of condensed phase material. So in the evaporation problem, we talked about the fact that it's a combined heat and mass transfer problem, and there's closure because of a thermodynamic relationship. And we're going to play on this sort of simple idea when we talk about this combustion problem. So we have, again, two unknowns in sort of this equation, and we close it with the thermodynamics. And in the combustion problem, it's more complicated. But the development is useful when we think about that the big problem in combustion problems is really, and from an analysis perspective, is the nonlinearity in the reaction term. So anything that we could do to remove that nonlinearity helps us from an analysis perspective. And one can identify, and the theory evolves in that the energy equation and species equations are coupled, and that we can actually create things called conserved scalars. We can develop scalar variables that are conserved, and conserved in the sense that there are no source or sink terms. So a conserved scalar is a scalar variable with no source or sink. So if you look, so we're going to go back, if you look at the fuel species equation and the energy equation as an example, in the fuel species equation, the sink term is this reaction rate term. In the energy equation, the source term has the same functional form, but it's multiplied by the heat of combustion. So at there are a couple of different things. I mean, a simple thing is if I multiply the fuel species equation by the heat of combustion, and then I add these two equations, that new equation that's constructed by adding this product of delta HC with the fuel species conservation equation summed with the energy equation should be conserved. So, and here I just divided by the energy equation by delta HC, and the terms that would have occurred previously would have been, again, we had a minus W dot triple prime F, but we're multiplying it by our W dot triple prime F delta HC divided by delta HC. So we lose that source sink term. Now, one thing you might say is, well, wait a second, I thought this had a thermal conductivity in it and this had a diffusivity in it. What happens there? Well, we are using the approximation here that this rho d is identically equal to K over Cp. Now, why would that be true? Well, d is the mass diffusivity. Okay, this d is the you know, you can think about it maybe as a binary diffusivity, or diffusivity into a mixture, into nitrogen, and you divide K over Cp by rho, and you get alpha, the thermal diffusivity. So they're both diffusivities, and oftentimes in mass transfer problems in combustion, we might make a Lewis number equal unity approximation. So the Lewis number is this alpha over d. So under those assumptions, we just have the same diffusivity for really an enthalpy type term and also for the species. So we can construct all sorts of conserved scalars in this system. Another one that couples fuel to temperature, we did. There's one that couples oxygen to temperature, and there's one that couples fuel to oxidant. Where this one is assumed to take place because of the stoichiometric relationship between the fuel and the oxidant. So let's just make sure that we're clear on that. This is the underlying chemical evolution that describes, you know, what interaction is required, but this can be interpreted as the fact that for every, so this is, say, the molecular weight of fuel. This is, remember, that's the stoichiometric coefficient. So this can be interpreted as saying for every n grams of fuel that are consumed, we consume YO grams of oxygen. So when we talk about W triple prime fuel, which is, again, F WF over some time and within some volume, we can relate this to the consumption of oxygen as this mass fraction of fuel times the amount of oxygen consumed when we consume a certain amount of fuel. So basically what I'm saying is that if I had this conservation equation now for the oxidant, I can multiply this, or I can divide this by nu O, WO, nu F, WF, and combine it with the fuel equation. So I think it's pretty obvious what I'm saying. So, for example, if I multiply this guy by nu O, WO over nu F, WF, I can combine these two equations and get a, say, YO. I'm going to call it, say, phi YF. So this thing would be conserved, okay? Okay, the mixture fraction sometimes is used in our descriptions in these combustion problems, and it's a conserved scalar value minus the value in the oxidant stream divided by the value in the pure fuel stream minus the value in the pure oxidant stream. And it's a useful construct for analyzing these problems. Okay, I think this is a good place to stop. We're going to take a break, and then we'll continue next time with some more developments in this diffusive burning process, and I think it'll be a nice transition to discussions of flame length, flame height, etc.